So today we are going to see Gauss divergence theorem, right? Yes. So this tells the relationship between the surface integral and the volume integral, right? So far what we have seen is first we have started with gradient, divergence and curl, and then we have seen some vector identities, and then we have solved lot of problems on line integral, and then we have seen a connection between line integral and double integral over s dou n by dou x minus dou m by dou y dx dy, which is line integral, which is Green's theorem, right? Yes. And we have seen surface integral and volume integral separately. Now we are going to see Gauss divergence theorem. So Gauss divergence theorem established a relationship between the surface integral and the volume integral, right? So what this theorem says is that the triple integral over v del dot f dv, So if f is any function, then triple integral over v del dot f dv is same as double integral over s fn ds, right? So this says that del dot f, so volume integral will not contain del, it will contain triple integral over v dv, f dv, but here we have del dot f. So if we have del dot f here, then this integral is same as the surface integral. That is what we are going to, that is what this theorem says, is that so triple integral over v del dot f dv is same as double integral over s fn ds. So first we need to find the volume integral, and then we need to find surface integral, and then we need to show that both are equal, right? And then we need to show both are equal. So you know how to find this integral, you know how to find this integral, because yesterday we have solved problems of how to find surface integral and how to find the volume integral. So yes, so straight away look into the problem, right? It's a very important problem. There is a chance that 60 to 70% that there will be question from Gauss divergence theorem. So the first question is again a very important question. So verify Gauss divergence theorem. Verify Gauss divergence theorem for f is equal to x square minus yz I vector plus y square minus zx j vector plus z square minus xy into k vector taken over the rectangular parallel pipe, taken over the rectangular parallelepiped such that 0 is less than x and a, 0 is y is less than b, 0 is less than z is less than c. So they are given bounds for the parallel pipe, right? Yes. So we need to verify Gauss divergence theorem. That means first we need to find the volume integral, and then we need to find the surface integral. So volume integral is very easy. So surface integral is very much little bit difficult, but if you practice 2 to 3 problems, it will be very easy for you, right? Yes. So first we will find the volume integral, right? So first we will find LHS. So what is LHS? So LHS is triple integral over v del dot f dv, and here you can see dv is nothing but dx dy dz, and what will be my del dot f? So we need to take divergence for this f. So for divergence we need to differentiate the first component with respect to x, second component with respect to y, and third component with respect to z. So we have this to be equal to 2x plus 2y plus 2z, right? The first component with respect to x, so 2x, 2y, 2z into, and dv is dx dy dz, dv is dx dy dz. Now they are given the limits for x, y, z. So x will be from 0 to a, y from 0 to b, and this is from 0 to c. So we need to integrate this, that's it, right? Yes. So we will integrate this. So I can take 2 outside. So if we take 2 outside, this will be integral 0 to a, integral 0 to b, integral 0 to c, x plus y plus z dx dy dz. Now first I need to integrate with respect to x, and then I need to dx, right? Sorry. So first we need to write x limit. So that means 0 to a, 0 to b, 0 to c. First I need to integrate this with respect to x. So we will have 2 times integral 0 to c, integral 0 to b. So when I integrate this with respect to x, so this will be x square by 2 plus yx plus zx integral, limit is from 0 to a dy dz, dy dz. Now I need to substitute upper limit and the lower limit. So when I substitute upper limit and the lower limit, we have integral 0 to c, integral 0 to b, and this will be a square by 2 plus ay plus az into dy dx. Right, so I am substituting upper limit to be a, so we have a square by 2 ya plus za dy dx. Now I need to integrate this with respect to y, right, I need to integrate this with respect to y. For that, what you need to do? So this will be 2 times integral 0 to c. Now I integrate this with respect to y, so a square by 2 will be constant. So integral dy is y plus a into, this will be y square by 2 plus again a z is constant, so we have only y. So limit is from 0 to b. So we have this is from 0 to b, 0 to b, 0 to b. Right? A z is constant, a square by 2 is constant, a is constant here. So this will be 2 times integral 0 to c. This will be a square b by 2 plus a b square by 2. Right? I am substituting upper limit to be equal to b. So we have this to be equal to b square by 2, and this will be azb into dz. Now I need to integrate with respect to z, and then I need to apply upper limit and the lower limit. So we have 2 times, so a square b by 2 is constant, integral dz is dz, the limit is from 0 to c, and ab square by 2 is constant, integral dz is z, so this will be z 0 to c plus ab, so this will be z square by 2 0 to c. So we need to apply upper limit and the lower limit. So this will be 2 times, so this will be a square bc by 2 plus ab square c by 2 plus ab c square by 2. Now I can take 2 outside and I can cancel this entire 2's, and if I take abc outside from here, so here we have a, there we have c, here we have c. Right, so if I am taking abc common in the numerator, so here we have 1a, here we have 1b, here we have 1c. So therefore the volume integral is abc into a plus b plus c. So we have found LHS. Now we need to find RHS. That means we need to find the surface integral. So ABC, a plus b plus c is our volume integral. Now surface integral is, you have to listen very carefully, right? So please make your attention. So we need to find double integral over s f n ds, f n ds, and they have given the surface to be equal to rectangular parallelepiped, right? Rectangular parallelepiped is same as a cube, right? So we can imagine both are same structure but a little bit. So rectangular parallelepiped and cube. Cube is a square. Cube faces will be square, and here will be rectangular parallelepiped. So we need to find the surface double integral over s f dot n ds. So what I am going to do is first we will make a diagram. So these are the 3 axes, and we need to this is our surface now, right? This is our surface now. Now I need to integrate So I need to find surface of this. What I want to do is I am going to mark this as O, and let this be A, B, C, D, E, and this is F, this is F, and this is C. Now what I am going to do is I am going to split this into 6 parts. Now how many faces are here? There are 6 faces. You can see the front side, back side, and then you can see there is a left, right, and top and down. So I am going to split this into 6 parts. So the front side, you can see the front side is D, E, F, G, right? D, E, F, G is our front side, and you can see our back side is O, C, B, A, O, C, B, A, and you can see the left side is O, C, D, G, and the right side is A, B, E, F, and the upper side is C, D, E, B, and lower side is O, G, A, F, right? O, G, A, F. So now we are going to find 6. We are going to split this into 6 parts, right? Front, back, up, front, back, left, right, up, down. So we are going to split this into 6 parts. Before that, you will make some. This is 0, 0, 0. So let us say this is our x axis, and this is our y axis, and this is our z axis. Now what this point will be? We are moving in y direction. So that means they are given the bound to be 0, a, 0, right? So we are moving in y direction. So we just change 0 to be equal to a. Now what will be this? So here you can see this is 0, 0, 0. Now we are moving in x direction, right? Now we are moving in x direction. So a, 0, 0. And here you can see we are moving in z direction. So 0, 0, a, right? Now from this, in order to find this point, you can see this point is a 0, a, 0. From this point we are moving x axis. That means we have to change x. So this will be a, 0, right? Already a, 0 is there. So we are moving from 0 to a because we are moving in x direction. And what this point will be? So this point is a, 0, 0. We are moving in z. So this will be a, 0, z. Sorry, a, 0, a. And what this point will be? So this point is 0, 0, a. So we are moving in y direction. So this will be 0, a. Alright, so we have to take this point to find this point. So from this point 0, a, 0, we are moving in z direction. So this will be 0, a. Both will get same answer. And this point is here 0, a. So we are moving in x direction. So this will be a, e. So these are the 8 vertices, right? So making vertices is very important. So I again repeat, this is 0, 0, 0. So first we are moving in y direction. So therefore we need to change y coordinate, and they are given the bound to be equal to a. So therefore 0, a, 0. And from here we are moving in z direction. So 0, 0, a. And here x direction a, 0, 0. And from these 3 points you can make all the points. From here we are moving in z direction. So a, 0, a. From here we are moving in y direction. So a, 0. So in that way we can make vertices for all the 8 points. Now we need to split. We are going to split this into front, double integral front, double integral back, and left, plus double integral over right, and double integral over up, and double integral over down. So good, we need to find 6 integral now. So first we will find front. So what is front? It is double integral over, our S is D, E, F, G. So D, E, F, G, F dot N, ds, right? F dot N, ds. And you can see now they are given f in the question, right? So we need to find n and ds. So in surface integral, how we will find n? Gradient of the surface divided by modulus of gradient of surface. and ds you can choose dx dy by n dot j or something you can do. But here what you will do is, so here we are considering only the front face, right? So here we are considering the first front face. So you just take n to be I, n to be I. For back face, n is equal to minus I, and for left face n is equal to j, and for right face n is equal to minus j, and for up n is equal to k, and for down n is equal to minus k. And here you have chosen n is equal to I, so you choose ds to be dy dz, right? dy dz. If you are choosing n to be j, you have to ds to be equal to dx dz. If you are choosing n to be equal to k, you have to choose ds is equal to dx dy, right? So this is the n and this is our ds. So what will be my f dot n ds? So our f is x square minus yz I vector plus y square minus zx j vector plus z square minus xy k vector, right? Now these are the conditions that we need to start with. N is equal to I and ds is equal to dy dz, and now we need to find the limits, right? We need to find the limit. So we are evaluating over d, e, f, g. So okay, let me first we will find d, e, f, g, f dot n ds. So this will be d, e, f, g, f dot n. So n is I and f dot n will be x square minus yz, and ds is dy dz, right? Now we need to find the limits. Now to find limit is, so you just take all the vertices. What is d? D is a comma 0 comma a, and what is e? E is a comma a comma a, and f is a comma 0, and g is a comma 0 comma 0, a comma 0 comma 0. Sorry. Actually the x bound is a, y bound is b, z bound is c, right? Okay, let me change this diagram. I have taken all the vertices to be equal to a. Actually x bound is a, y bound is b, z bound is c. Okay, this is right. So now let me draw all the vertices once again. So I have taken all the bounds to be equal to a, but our question is the bound for x is a, and bound for y is b, and the bound for z is c, right? So let me draw the diagram again. So here we are moving in x direction, and the bound for x is a, so a comma 0 comma 0, and here we are moving in z direction, so it will be 0 comma 0 comma c, right? Because for z bound is c. And here we are moving in y direction, so that means 0 comma b comma 0, right? 0 comma b comma 0, and you can find this point, right? So this is a comma 0 comma 0. We are moving in z direction, that means we need to change 0 to be equal to c, and this point is d, and we are moving in y direction. So this is a comma b comma c, and this point is a comma 0 comma 0. We are moving in y direction, so this is a comma b comma 0, a comma b comma 0, and this point is 0 comma b comma 0. We are moving in z direction, this point is 0 comma b comma c. So these are the 8 vertices, right? So I first have taken all the bounds to be equal to a, but here whenever you are moving in x direction, you take a, y, b, z, c. Now, so what is our d now? Our d is a comma 0 comma c, and our e is a comma b comma c, and our f is a comma b comma 0, and our g is a comma 0 comma 0. Now we need to find y and z, right? You can see x is constant for all. So x is equal to a, and you can see y varies from now you can just take, you can just vary y and z. So we know y varies from 0 to b, and we know z varies from 0 to c. Yes, right. So you can see x is equal to a, and y and z are varying, and it is already we know that y varies from 0 to b and z varies from 0 to c. So this integral will be, so y limit is from 0 to b, z limit is from 0 to c, and here x is a, it will be a square minus yz dy dz. So this will be integral 0 to c. So integration with respect to y, so this will be a square b, right. So we have integral dy here. So when I substitute upper limit, we will have b, so a square b minus z. So derivative of integration of y is y square by 2, and when I substitute limit, we have b square by 2 into dz, and you can see there is no z here, there is no z term. So we have a square b is constant, integral dz is z, upper limit is c minus, and we have b square by 2 as constant, and the integration of z is z square by 2. So z square by 2, when I apply limit, we will have c square by 2. So we will have this value to be equal to a square bc minus b square c square by 4. Okay, so this value is a square bc minus b square c square by 4. Now we need to find back. So for back we will have, so first we are going to find back. So for back you can see O, what is this point? This point is C, right? So for back our area is 0 OCBA, and our n is minus I, right. Our n is minus I, and ds is same as dx dy dz, ds is same, dy dz, and f is here, and this will be minus, right. This will be minus. Right, this is minus, and we need to find limits now. So for finding limits, we need to this will be, so we are evaluating over OCBA. So OCBA, so O is 0, 0, 0, and C is 0, 0, C, and B is 0, B, C, and A is 0, B, 0. Now here you can see x is equal to 0, right, 0, 0, 0, 0. The previous one x is equal to A, here x is equal to 0, and we are varying y and b. So y varies from 0 to b, z varies from 0 to c. So this integral will be integral 0 to c, integral 0 to b. We have only y is z, right. So x is 0, and we have minus of minus is plus, so dy dz. So we have this term to be equal to, so we have only b square c square by 4, right, because I already found that this value is b square c square by 4. So this value will be b square c square by 4. So this will be, when I integrate first, z is constant, so z y square by 2. So when I apply the limit, you will have z b square by 2, and again if you integrate with respect to z, we will have b square z square by 2. When you apply the upper limit, you will have b square c square by 4. So this value is b square c square by 4. Now we need to find left hand side. So left hand side, you can see this is AB, okay, A, B, E. Okay, first we will move on right and then left. So right is A, B, E, F. Okay, first we will move on right and then left. So for right hand side, you have to take n to be equal to j, and so let us go on right. So this is right hand side. So for right hand side, this is A, B, E, F. So A, B, E, F, A, B, E, F, and our n is j vector now. Our n is j vector, and this is dx, dz. If you are taking j, you have to take other components dx, dz. So what will be my f dot n ds? So f dot n ds will be, we will have, f is this and our n is j now. So this will be y square minus zx dx dz. Now we need to find the limits, right? We need to find the limits. So what is the right hand side? Right hand side is a, b, e, f. So for a, b, e, f, so what is a? A is 0 comma b comma c, 0 comma b comma 0, and b is 0 comma b comma c, and a comma b comma c, and a comma b comma 0. Now you can see y is b, right? So y is equal to b, x and z are varying. So x varies from 0 to a, z varies from 0 to c. So this will be, so this value will be integral. So we are first adding z, so that means 0 to c, 0 to a, 0 to c, 0 to a, y square is b square minus zx dx dz. So again when I integrate this, we will have integral 0 to c b square a, because integral dx is x, this will be a, minus z into x square by 2, so upper limit will be a square by 2. So when I again integrate, with respect to dz, we will have b square a as constant, integral dz is z, so we have c, and here we will have z square by 2, so we have a square c square by 4. So this value is b square ac minus a square c square by 4. Now we need to go on, we need to find left hand side. So left is minus j, this will be minus of y square minus zx, right, because we have minus j. So we need to find limits now. So left hand side is OCDG, and this will be OCDG, and you can see OCDG. O is 0 comma 0 comma 0, C is 0 comma 0 comma C, and A comma 0 comma C, and A comma 0 comma 0. You can see y is equal to 0. So y is equal to 0. X and z are varying. So this will be, we will have only minus zx, because our y is 0, and this will be plus, right, because we have minus of minus. So when I integrate this, we will have only this term, this term, there will be no term. So we will have a square c square by 4. So this value is a square c square by 4, right, a square c square by 4. Now we need to find up and we need to find down. So we will find up. So up. So up is DCEB. So DCEB, and you have to choose n to be equal to k, and dx will be dx dy, and what will be my f dot n? F dot n will be f dot k, so it will be z square minus xy dx dy. Now we need to find the limits. So So you can see OCDG. So OCDG, DCEB. So for DCEB, so what is D? We are finding up. So AOC and ABC and A0BC and 00C. You can see Z is equal to C, and X varies from 0 to A, Y varies from 0 to B. Y varies from 0 to B. So therefore, this value will be integral 0 to B, integral 0 to A, and z square minus xy, this is c square minus xy dx dy. Now again we need to integrate this. So this integral 0 to B c square A, so this will be minus y a square by 2 into dy. So this will be x delta y, and we need to integrate with respect to y. So we have c square AB minus a square b square by 4. So this value is I write here. So up value is c square AB minus a square b square by 4. Now we need to find down. So down is minus k, and this will be minus of z square minus xy, and for down you can see z is 0, right, 0 0 0 0, and z is 0 here for down. So for down OAGF, and in OAGF z is equal to 0, x varies from 0 to A, y varies from 0 to B. So this value will be, so here we don't have 0 and this will be plus, so we don't have this value, this will be plus, and we don't have this value and this will be plus. So we have the down value to be equal to a square b square by 4. So we have found up down, we have found all values, right. So now we need to find double integral over S f dot nds. Therefore double integral over S f dot nds is equal to, you add up all the values. So we have a square b square minus b square c square by 4, this is front side, plus b square c square by 4, this is right and back side, plus right side is b square ac minus a square c square by 4, plus the left hand side is a square c square by 4, plus the upper c square ab minus a square b square by 4, and down is a square b square by 4. So when I simplify this, you can see this to get cancelled. So we have a square bc plus b square ac plus c square ab. Now if I take abc common, we will have a plus b plus c. So therefore the volume integral del dot f dv is same as the surface integral double integral over S f dot nds. So we have verified the Gauss divergence theorem, right. So very important problem. So in exam point of view, they will just alter ABC. So in exam they will give 1 comma 1 comma 0. So they will only alter the bounds, right. So we will do one more problem now. Before that I will fill the ink. So we'll do one more problem. So verify divergence theorem. Verify divergence theorem. Verify divergence theorem for to understand the first problem. Then you can read f is 2x minus z I vector plus x square y j vector plus minus x z square k vector taken over the region bounded by z is equal to 0, z is equal to 1, x is equal to 0, x is equal to 0, x is equal to 1, and y is equal to 0, y is equal to 1, z is equal to 0, z is equal to 1. So instead of a, b, c, here we are going to have everything to be equal to 1, right? So everything in the previous problem we have x bound is 0 to a, y bound is 0 to b, z bound is 0 to c. So here we have x bound to be 0 to 1, y bound to be 0 to 1, and z bound to be 0 to 1. So first we need to evaluate the volume integral, and then we need to evaluate the surface integral, and then we need to show that both are equal. So you can easily draw the diagram. So it is every bound is 1, right? So this point, this is our x-axis. This point will be 1, 0, 0, and this point will be, we are moving in y, so it will be 0, 1, 0. So in previous problem we have written 0, b, 0 because y bound is b. Here y bound is 1. So this is nothing but we are doing it z. So we have 0, 0, 1. And for finding this point, we are moving in from here. We are moving in this point is 1, 0, right? This point is 1, 0, and here we are moving in z. So we have 1, 0, 1, and this point will be 1, 1, 1. And from here to here we are moving in z. So we have 0, 1, 1, and from here to here we are moving in y. So we have 1, 0. These are the 8 vertices. So before that we will find volume integral, right? This is required only for surface integral. So first we will find a LHS. So LHS is triple integral over V del dot f dv. So this will be triple integral. So we need to find divergence. So first component with respect to x, so we have 2, plus second component with respect to y, so we have x square, and third component with respect to z, we have 2xz. So 2 plus x square minus 2xz, and our dv is dx, dy, dz, and you can see the limit is everything is from 0 to 1. So we integrate this, right? So integral 0 to 1, integral 0 to 1. So 2 times, so when I integrate dx, so we will have x, so it will be 1, and it will be x cubed by 3. So x cubed by 3 will be 1 by 3, and here we have minus 2z is common, and integration of x is x square by 2, and after limit we will have 1 by 2 into dy dz, and you can see this y z2 will get cancelled, so we have only z here. Now we need to integrate this with respect to y. So this will be integral 0 to 1. So here again no y, so it will be integral dy. Integral dy is y. Again the limit is from 0 to 1. Again here we have only 1 here. And again we don't have y. So this is also be 1 dz. So z into integral dy. So dy is y. Upper limit is 1. So this will be, so when I integrate with respect to dz, so again here we will have 1 because 2 dz. So z, here we have again 1 by 3 into 1 minus this will be z square by 2. So we have 1 by 2. So we have 2 plus 1 by 3 minus 1 by 2. So 2 plus 1 by 3 is 7 by 3 minus 1 by 2, and this will be 40 minus 3 by 6, which is 11 by 6. Yes, so 11 by 6 is our volume integral, right? Now it's the volume integral. Now we need to find the surface integral. Note down the answer, 11 by 6. So again, I will be going fast this time. So I am going to follow the same technique: front, back, left, right, up, down, right? So this will be double integral over s, f dot n ds will be double integral front plus double integral back plus double integral right, double integral left, double integral up, double integral down. So we will find one by one. Let us give some space here for the answers. So first we will find front. Right, so that means double integral over s, f dot n ds. So you just make down the s, right? Front is this is our a. So a d e f. This is our, sorry, this is what point is this? This point is e, right? A b c d, sorry, this point is g. Okay, so we can make the face here. Front face is d e f g. And our n is I, and our ds is dy dz, and you can see for this phase x is equal to 1, right? So x is equal to 1, so 1 1 1 1, x is equal to 1, and y and z are varying. So y varies from 0 to 1, z varies from 0 to 1, same as previous problem. Sorry. I forgot to wear mic. Sorry. Yes, sorry. So I think it will be not visible. It will not be hearable. So okay. So far what we did is we have been verifying the Gauss divergence theorem for this. First we have found the volume integral. So for volume integral, you can see how the vertices I have marked. In the previous problem, so I'll repeat the steps what I have did, right? So I think mic will not clear. So in the previous problem, we have x bound is 0 to a, y bound is 0 to b, z bound is 0 to c. So if we are going in y direction, we will change y to be equal to b, and we are moving in z direction, we will change z to be c. But here you can see the bounds are, everything is bound is 0 to 1. So we have started at 0, 0, and we are moving in a y direction. So that means we are changing 0 to equal to 1, and we are moving in x direction. So we are changing 0, 0 to 1, 0, 0. And from here we are moving, from here to here we are moving in z direction. So we are changing 0 to be equal to 1. So 0, 0, 1. And we need to find all other points. So from here to here we are moving in z direction. So 1, 0 will remain as it is, z will be changed to 1. So we have 1, 0, 1. And from here to here we are moving in y direction. That means 0 will be changed to 1. And here to here we are moving in z direction. So that will be changed to 0, 1, 1. So we have found the volume integral, and the volume integral answer turns out to be 11 by 6. Now we need to find the surface integral. To find the surface integral, we need to make front, back, right, left, up, down. So first, that's what I written here: front, back, right, left, up, down. So first, for finding front, n will be I, and for back n will be minus I, and for right n will be j, and for left n will be minus j, and for up n will be k, and for down n will be minus k. So first I am finding f front side, and you can see for front side is d e f g. You can see x is equal to 1, right? X is equal to same number, y and z are varying. So x is equal to 1, y and z are varying. So what will be my double integral over s f dot n ds? This is f dot n is I, and our f is 2x minus when you make a dot product with I, so we have only 2x minus z, and our ds is dy dz, and y varies from 0 to 1, and also we have x to be equal to 1. So this value will be integral 0 to 1 2 into 1. So we will have only 2 minus z dy dz. So when I integrate this, we will have 2 times, so this will be integral 0 to 1. So when I integrate with respect to y, so we have 2 into 1 minus z into 1, because both the terms does not contain y, into dz, and again 2 does not contain 1. So we have 2 into 1 minus z square by 2, which is 1 by 2. So this value is 2 minus 1 by 2, right? This value is 2 minus 1 by 2. So this value is, we will keep this as it is, right? So this will be very easy for us to cancel out, right? So don't take LCM. So just take this value to be equal to 2 plus 1 by 2. This is our front. Now we need to find back, and for back you can see OCBA, x is equal to 0, right? Everything follows same pattern, right? So this won't change, right? For the previous problem, here problem, same. Okay, so you can see for the back side x is 0, and y and z are varying. So that means we will have 2 into 0. That means there won't be this term, and n is minus, so this is back side, and for back side our n is minus I. So you can just change s to be equal to OCBA, right? OCBA, and this will be, here we have minus here, and if substitute x is equal to 0, this will be plus, this will be, we won't have this term, and this will be plus, and we will have only 1 by 2, right? Here again we don't have this term. So answer will be 1 by 2. This is for back. Now we will find right hand side. So right hand side, our n is j, and our ds is dx dy. ds is dx dy, and you can see for right hand side, y is equal to 1, x and z are varying. So we have y is equal to 1 and x and z are varying, dx dz, x and z are varying, x varies from 0 to 1, y varies from 0 to 1. So what will be my f dot n ds? So our f dot n ds will be, so n is j, so f dot j will be x square y, ds is dx dz, and you can see y is 1, so we have this to be integral 0 to 1 x square dx dz. So when I integrate this first with respect to z, x, we will have x cube by 3, the limit is from 0 to 1 dz, and when I substitute, so we will have 1 by 3, again I can take 1 by 3 outside, so integral dz is z, and upper limit minus lower limit, so we have 1 by 3, right? So therefore the right hand side is 1 by 3. Now you will find left hand side, and you can see for left hand side, y is equal to 0, and x and z are varying, and n will be minus j. So this will be minus of x square y, and since y is 0, this entire term will be 0. So therefore our left hand side will be 0. Now we will find up. So for up, our n will be k vector, and our ds will be dx dy, and you can see for up, you can see z is 1, x and y are varying, so our f dot n ds will be this will be integral f dot n. So f with respect to k. So we have minus, we already have minus here. So minus xz square dx dy, and you can see x varies from 0 to 1, y varies from 0 to 1. Now z is 1, so we have this to be double integral 0 to 1, 0 to 1 z x square dx dy, x square dx dy. So when I integrate this, we will have, so minus integral 0 to 1, so x square is x cube by 3, so x cube by 3 upper limit is 1, so we have 1 by 3, and this will be minus 1 by 3. So this will be minus 1 by 3. Now we need to find down. So for down n is minus k, and you can see for down z is 0, right, z is 0, so z will be 0 and this entire term will be 0 because we have x into z square. So we have found all the terms. So this is 0. Now we need to just make some substitutions, simplifications. I think I made some error in some, actually what we have got, this is 1 by 2 is right, and this is 3 by 2, so this is also right, and right is 1 by 3, right, and for minus j it is 0, right, this is also right, and for this is 1 by 3, this is also right, and for this 0, and this is minus 1 by 2. So actually we are getting this as minus 1 by 2. Actually we are getting this answer as minus 1 by 2. Minus 1 by 2. So we will verify this answer again. So for up, we have n to be equal to k and ds to be dx dy, and double integral over s f dot n ds will be double integral 0 to 1. So it will be minus x z square dx dy. So for this z is equal to 1. Okay. Actually I have written some mistake, I think. So it will be minus integral 0 to 1, integral 0 to 1 x dx dy. It is not x square, right? So when I was writing, when I was finding values of up, I made some mistake. So this will be x square by 2. Yes. So answer is minus 1 by 2. Right? It is not 1 by 3. It is minus 1 by 2. I written x square here. So just by mistake, written x square. So it is x dx. Right. So we are getting minus 1 by 2 as this answer. Now we need to simplify this. So when I simplify this, you can see this minus 1 by 2, this plus 1 by 2 will get cancelled. So overall we have 2 plus 1 by 3 minus 1 by 2. So this is 7 by 3, this is 1 by 2, and this is 14 minus 3 by 6, so which is 11 by 6, which is same as the volume integral triple integral over v del dot f dv, right. So we have verified the Gauss divergence theorem. So third problem, the only thing that will be changed is the bounds, right. So depending upon the bounds, you just change the values. So maximum it will be A, B, C, or now you just try with the bounds. So let me give one exercise problem. So you just try with the bounds everything to be equal to A. Everything to be equal to A. This take this exercise. So you just take the F to be equal to the same F that we did in second problem. You take the bound to be equal to everything to be equal to A. So in the previous problem we have everything to be equal to 0 to 1, 0 to 1, 0 to 1. So you just take this bounds and you try to do the problem in your own, and whether you will get try whether you are getting the surface and volume integral are same. So third problem is, if f is equal to 4xz I vector, 4xz I vector minus y square j vector plus yz k vector, and S is the surface bounded by, and S is the surface bounded by, S is the surface bounded by x is equal to 0, y is equal to 0, z is equal to 0, x is equal to 1, y is equal to 1, z is equal to 1. Evaluate double integral over S f dot n ds. So they haven't said to verify Gauss divergence theorem. So this is our question. So we need to evaluate the surface integral. So by evaluating surface integral, what you can do, you can use you can split this into 6 phases that I have said, right? In order to evaluate this, they are only asking us to evaluate this, right? So that means you need to split this into 6 phases, and then the bound is 0 to 1. You can do by that, or if we need to only find this value, right? By finding volume integral is very easy when compared to surface integral. So in order to evaluate this, so by Gauss divergence theorem, double integral over S f dot n ds is same as triple integral over V del dot f dv. So by evaluating this will take much time when compared to this, that is volume integral. So you don't need to find all the 6 phases and then you need to add up. So we only need to find this value. So by Gauss divergence theorem we know that this value will be equal to del dot f dv. So we will find this value, and we say that the value for this also triple integral over V del dot f dv. So we will find only triple integral over V del dot f dv. So what is triple integral over V del dot f dv? So in exam, if they give some bounds like this, and if they ask us to find the surface integral, you can use Gauss divergence theorem, and you can find only del dot f dv. So this is del dot f dv. So you can see every bound is 0 to 1. And del dot f is, you need to find the divergence for this. So first with respect to x, so we have 4z, second with respect to y, and third with respect to z, so we have again y into dx, dy, dz, or dz, dy, dx. And you can see minus 2y plus y is minus y. So we only evaluate triple integral over V 4z minus y dx, dy, dz. And you can see this will finish in 2 or 3 minutes when compared to finding the surface integral. So I think you can evaluate this, right? So this will be integral 0 to 1, this will be integral 0 to 1. Here we don't have x term, so 4z minus y will be constant into 1 dy dz, and when you integrate with respect to y, so we have 4z, and integration of dy is y, so we have 1. So here we have 1 by 2 dz, so integral y minus y dy is y square by 2, and when you integrate with respect to z, so 4 z square by 2, z square is 1 by 2, and in 1 by 2 we don't have z. So this will be 4 by 2 minus 1 by 2, which is 3 by 2. So therefore 3 by 2 is our required answer. So you can see we have finished this problem in less than 1 or 2 minutes when I use the Gauss divergence theorem. So in order to evaluate this, we can evaluate 3 by 2. But in the exam, if they suppose if I change this question to verify Gauss divergence theorem, that means you need to find a 3 by 2, and then you need to evaluate this also, right? You take this as exercise, you evaluate this by finding all 6 spaces, and you add up all 6 spaces, you will get 3 by 2 as an answer. So in this problem they ask us to evaluate, but in exam if they give the same f and they give the same bounds, if they ask us to verify Gauss divergence theorem, means what you need to do? You need to find triple integral del dot f dv, and you need to find double integral over s f dot n ds. So I will give you one more problem for exercise. Evaluate the fourth problem is evaluate double integral over s for xz Okay, this is not a problem. So I'm going to do the fourth problem. So evaluate double integral over s f dot n ds, where f is equal to x y I vector plus z square j vector plus 2yz k vector over the tetrahedron, very important problem, over the tetrahedron bounded by the plane x is equal to 0, y is equal to 0, z is equal to 0, and x plus y plus z is equal to 1. That means we need to evaluate over tetrahedron. Now in order to find double integral over s f dot n ds, I am going to find using Gauss divergence theorem. Actually, whenever you have this condition, is always a parallel pipe. This will always be a parallel pipe, right? So whenever you have 0 less than x less than a, 0 y less than b, 0 less than c, you will always get a parallel pipe. This is a condition for a parallel pipe. So over the tetrahedron bounded by the plane, so this is a condition for parallel pipe. Suppose if they haven't said that surface is a parallel pipe, but if they given this condition, means you should always think that of as a parallel pipe, right? If this is the case, we will have square or rectangle. If I include third dimension, we will have a cube, right? So if in cube it will be like this, in parallel pipe you will have some like this. That's it. Now in order to evaluate the double integral over s f dot n ds, we will evaluate triple integral over v del dot f dv. So del dot f dv will be triple integral over del dot f. So del dot f is first component with respect to x, second component with respect to y. So second component we have 0, third component with respect to z. So we have 2y. So we have 3y overall. So 3y dx dy dz, and we need to find the x limit, y limit, z limit, and you can easily find, as I always say, I have actually said that we have already found how to find the limits, right? So for x limit, put y is equal to 0, z is equal to 0. That means x varies from 0 to 1. X varies from 0 to 1. To find y limit, put z is equal to 0. So z is equal to 0. That means y varies from 0 to 1 minus x, and for z limit, z varies from 0 to 1 minus x minus y. So we will change this to dz dy dx, and x varies from 0 to 1, y varies from 0 to 1 minus x, and this xz varies from 0 to 1 minus x minus y. Now I think you can easily do this. So you just need to evaluate a triple integral. So I have mentioned the limits. So it is 3y dz dy dx. So we already in the yesterday classes I have said how to find the limits when I have a plane like this. So for finding x limit, put y is equal to 0, z is equal to 0. So you have x to be equal to 1. For finding y limit, you put z is equal to 0. We have y is equal to 1 minus x. And for z limit, you just bring all the terms to that side. So we have z is equal to 0 to 1 minus x minus y. So we need to integrate this. So this will be integral 0 to 1, integral 0 to 1 minus x. 3y is constant, and integral dz is z. So we have 1 minus x minus y and dy dx. So I think you can do this, right? No, I am not going to do this. The answer you will get will be 1 by 8. The normal basic problem. So answer will be 1 by 8. So I will do 2 problems for you to exercise. Okay, I will give you some more problems for exercise. Actually very easy, all are same. You just have to use triple integral, that's it. So exercise problems. The first problem is verify Gauss divergence theorem. Our f is 4xz I vector minus y square j vector plus yz k vector over the cube, taken over the cube and parallel by more or same, right? Taken over the cube, x is equal to 0, x is equal to 1, y is equal to 0, y is equal to 1, z is equal to 0, z is equal to 1. So you just have to verify Gauss divergence theorem. You need to find the triple integral, and then you need to find the volume into surface integral. You need to find triple integral over p del dot f dv and double integral over s f dot n ds. You can see the bounds are 0 to 1 and f is 4xz I vector minus y square j vector plus yz k vector. You will get both the answer to be equal to 3 by 2, right? You will get the volume integral to be equal to 3 by 2 and as well as surface. So second problem is evaluate double integral over s x square dy dz plus y square dz dx plus 2z into xy minus x minus y dx dy, where s is surface of the cube, 0 less than x less than 1, 0 y less than 1, 0 less than 1. You don't worry about dy dz dx dy, right? So in order to find this by Gauss divergence theorem, we can evaluate triple integral over v del dot f dv. You don't omit dy dz dx and dx dy. You just consider x square, y square and this as z square coefficient. This as our I vector coefficient, this is j vector coefficient and this is k vector coefficient, right? This is dy dz is same as I vector component and dz dx is same as j vector component and dx dy is same as k vector component. So this is same as x square I vector plus y square j vector plus 2z into xy minus x minus y k vector, right. So both are same. So in order to find this, you just find the divergence. So for divergence will be 2x plus 2y, 2x plus 2y plus xy minus x minus y, right. So you will get divergence to be equal to xy. So when you make a divergence for this, so this will be 2x, this will be 2y, this you have differentiated with respect to z, so z will be 1. So we have 2 into xy minus x minus y. So when you get simplification, you will have xy as your divergence, and you can see limits is from 0 to 1, 0 to 1, 0 to 1. So in order to evaluate, we can evaluate this by Cauchy divergence theorem. You will get answer to be equal to 1 by 2. And third problem is evaluate double integral over s 4xz dy dz minus y square dz dx plus yz dx dy. Again dx dy dz is same as I vector, dz dx is same as j vector, and dx dy same as k vector. Same question, right. X is equal to 0, the same bounds, the only thing is f is varying here. So here f is 4xz I vector minus y square j vector plus y square k vector. So we will get answer to be equal to 3 by 2, right. So don't get confused if you have dy dz, dz dx and dx dy, right. It is same as I vector, j vector and k vector. So I will give you one more problem also. So fourth problem, this is the third problem, and the fourth problem is evaluate double integral x cube minus yz I vector minus 2x square y j vector. Okay. Use Gauss divergence theorem to prove that at this value plus 2k vector n ds is equal to a power 5 by 3, and the bounds are x is equal to 0 to a, y is equal to 0 to a, z is equal to 0 to a. So we need to show that by using Gauss divergence theorem, we need to show the double integral over s f dot n ds. So they are given f to be equal to x cube minus yz I vector minus 2x square y j vector plus 2k vector. We need to prove that this value will be equal to a by 5. So what we can do? You can just find a divergence for this, so which will be 3x square, and here with respect to y, so minus 2x square, and here with respect to z, so we have 0. So we will have only x square only, right. 3x square minus 2x square is x square. The limit is from 0 to a, 0 to a, 0 to a, dx, dy, dz, and you just prove that the value is equal to a power 5 by 3. I think there are many problems in the textbook, you can do any problem. So after finishing these 4 problems, you just refer the material that I have given. So just refer page number 100 to 120. Page number 100 to 120, you will have Gauss divergence theorem as a topic. You can refer for more problems also, right. Yes. So tomorrow we are going to see Stokes theorem, right. Stokes theorem, and then a Ferret-Serret formula. So syllabus will be completed, right. So in next 2 to 3 classes, syllabus will be completed. So you have to practice more problems, and you practice these problems, and you practice more problems in the textbook, right. So that's it. Thank you.